Right, so I'll share my screen. Hope my screen is visible. Right. Yeah, so today we'll learn about disjoint set union. It's called DSU or union find. Right, in lead code it's called union find. In all other places they call it DSU. Right. So basically DSU is an algorithm. Okay. It's an algorithm to very quickly merge related components together. Right. And it does it really quickly. Right. Or basically you can say it makes a set of elements that share some common property. Right. And how is that useful? We'll see that in questions. Right. But right now just try to understand. Right. So we start with let's say every number is in itself a set. Let's say 1, 2, 3, 4, 5. Right. So every number in itself, let's say, is a set starting off with. Right. So what we want to do, we want to merge few of them. Like let's say we want to merge 1 and 2. So we say that okay, 1 is merged with 2, so 1 is a parent of 2 for now. Let's call it parent. Right. And every time we try to merge, right, we merge it with its parent, or you can call its representative. Right. So now instead of having 5 sets, we have 4 sets, and 1 and 2 are merged. Similarly, you can merge other numbers as well. Right. Let's say you merge 4 and 5. Right. Now the number of sets decrease to 3. Right. Here it was 4. Here it was 5. So every merge decreases the number of sets basically. Right. And now let's say you want to merge. See, you want to merge 5 and 2. So instead of merging 5 and 2, you merge their representatives basically. Right. And this all boils down to a tree problem basically. Right. So 4 becomes a child of 1. Remember 1 and 4 were the representatives of those set, right? So we make something like this out of it, and 5 is already a child of 4, right? Now can you realize that if 4 was a very big set, instead of merging every single number with, let's say, 2, we can directly merge its parent, its own representative, with 2's representative, and basically we have merged the entire set in itself. I'll just reiterate everything again. Right, guys, please be on time. So DSU is a problem where we merge similar elements together, right? So let's say we are starting off with every element being a set of its own, right? Let's say 1, 2, 3, 4, 5, and all the elements are a set of its own, right? So initially we have 5 sets to begin with, let's just say. Let's say you want to merge 1 and 2. Right now each set is a representative of itself, right? So what we want to do is we want to merge 2 with 1. So we merge the representative of 2 with representative of 1. Let's say, or we call this parent. We call the representative as parent, right? So you can call it set, you can call it parent, it doesn't matter, right? So we make something like this when you merge. We make 2 as a child of 1, right? And 3, 4, 5 remains the same. Now if you want to merge 5 with 4, same process. Now if you want to merge 5, okay, wait, remember this is the process of merging 2 with 5. So we merge the representative of 2 with representative of 5, or basically parent of 2 with parent of 5. So 1 can become a child of 4, or 4 can become a child of 1. For now, we'll make some improvements here, but right now just understand this. Now can you see that all of these are merged? Can you see that all of these represent the same set? Now if you ask me what is the parent of 5, I will not say 4, I'll say 1. Parent of 4 is also 1. Parent of 2 is also 1. Basically the root of that tree, right? You can always see DSU as a tree. So In short, representative or parent is actually the root of that entire tree, right? Still 3 is not merged. Now if you want to merge 3 and 4, tell me how the tree will look like now. Now you have to understand that you are not merging elements, you are merging their representatives, or basically parent. Parent of 3 is 3. Parent of 4 is 1. Right, so basically you are merging 3 with 1, so this becomes a set. Right, now how do you verify that 5 and 3 are in the same set? Basically you compare their parents, no? Or you find their set. You find set of 5 which is going to return 1 because 1 is the root of this tree. You find set of 3 which is also going to return 1. Hence you can say that both of them represent the same set, or both of them are in the same set. Right. So any doubts there? This is just theoretical explanation. I will jump to code.
When you merge 1 and 2 and 5,
Yeah.
the representative selected can either be 1 or 4, right? Or is there any rule for that?
We'll talk about that. Right now just make it random.
Okay, cool.
Okay.
So like either of the two parents, basically.
Yes, right for now. For now. Don't
Okay,
don't stick to it. We'll change that. We'll change it really
okay,
soon.
cool.
Right. Right. So this is just very basic explanation of DSU. So whenever you want to merge two things, you pick both their representatives, you merge them. Right. Always remember that I am not merging. If I am merging 1 and 2 and 4 and 5 and I am to 1, 5 and 2, I am not doing something like 2, 5, 4. Right. This makes no sense. You always pick their parent. Right. I am not doing something like this as well. Remember, I am merging it with the representative or their parent, right? And it might seem very intuitive because this will decrease the size of the path, right? Let's say you want to find the parent of 5, you go to 4, you go to 2, you go to 1. So this is a bigger path, no? A smaller path will be directly attaching it here, right? So this decreases the number of iterations required to find the parent, right? So this is correct and this is wrong, this is wrong, this is also wrong, right? 1, 2 and 3 are wrong, 4 is correct, right? For now this is the naive implementation, this is a naive way of doing it. Right, any doubts until here? It's just theoretical for now. Now we'll see what the naive implementation is. Right, so initially it's make set, so we use the parent array. So parent of every element is itself, right? Initially how we started, 1, 2, 3, right? So parent of 1 is 1, parent of 2 is 2, and so on, right? When you find the set, now can you understand this condition? What is the root? What is the root of that set whose parent is itself, right? This is the root of itself. Now if you want to make a tree like this, let's say 1 and 2 is inverse. What is the parent of 2? It's 1. What is the parent of 1? It's also 1. So you know that this is a root, right? Another example, we merged 1, 2, 4, 5, right? Now understand parent of 5. Okay, right now, okay, right now parent of 5 is 4 right now. Okay, I'm not talking about representative. Okay, it's 1, but right now we don't know, we just know this, right? Parent of 4 is supposed to be 1, parent of 1 is 1 itself, right? I know I told that parent of 5 is 1 initially, or representative, we'll come up to that, but right now just look at the tree, just understand the tree. In the tree 5 is still attached to 4, right? So 5 just knows that okay, my parent is 4 for now, right? And parent of 2 is 1. Now the only node where parent of x is x itself is the root. It's always the root, right? So can you understand that you can recursively climb the tree like this? right? If you want to find parent of 5, first you see what its parent is. Is it parent equal? No. Then you find the parent of 5 basically, right? Yeah, parent of 5 basically. So that means parent of 5, or let's say, let's not confuse it. Let's say find representative. Okay. Let's say you want to find the representative, or we call it find set. So you want to find the set of 5. Okay, so to find the set of 5, you check is the parent of 5 equal to 5. That is only happens when this is the root of its own set, or this is the representative, right? So let's say find representative. So if parent of 5 is not 5, what we do, we basically return find representative of whatever its parent is, right? So basically 5 tries to poll 4, right? 5 polls 4 and asks, okay, you find your set and tell me, right? So 5, its parent is not 5 itself, it's 4. So it asks 4, can you tell me what your parent is? Find, let's say, find representative of 4. Now 4 says, okay, I am also not my parent, I'll ask my parent. It's 1, right? So it says, okay, find representative of 1, right? Now 1 will say that, okay, my parent, I am my own parent, right? So it will return 1, right? This will return 1, and you'll say that, okay, find set of 5 is 1, right? So this is how you fetch your representative, or sorry, find representative, right? So basically you climb the tree, and this is the I think third kind of tree implementation that I taught you yesterday, right? Where instead of storing edge pairs or adjacency list, you just store what your parent is basically, right? So 1 2 4 5, right? 3. The way to represent this tree in terms of parent array is, let's say 1 2 3 4. So 1's parent is 1, 2's parent is 1, 3's parent is 3 itself, 4's parent is 1, 5's parent is 4, right? Now can you see that you can climb the tree? To find the root of, let's say, some tree, you go to 4, and 4 goes to 1, and 1 goes to 1 itself and says that, okay, I am the root. Similarly 2 goes to 1, 1 goes to 1 itself, says I am the root, right? So did you understand the find set function? Find representative, find set, whatever, right? Can you see that it's just recursively trying to find itself, unless its sole parent is just recursively finding itself, calling itself again.
Yes, for a given tree, the parent or like the representative is going to be the same for all nodes, right?
Yes.
So we can just find for one, and then we can say, okay, this is for all. Will that work?
Sorry, we can find for any. Yes, you can find for anyone.
And then yeah, that's it. Okay.
Yeah. But the thing is, right now you don't know, right? You have to check.
Yeah,
Basically,
understood.
find set of 5 is equal to find set of 2, but you don't know that. You have to check that first.
So worst case मतलब n तो लगेगा ही लगेगा.
Yes,
Worst case
yes.
in dispute thing.
Worst case is n. So, okay, that's for find set. Now, when you try to union set, right? As I told you, first you find the representative, right? So you find the representative of A. Let's call representative. Now, please understand that representative is not necessarily equal to parent. Parent is the direct, how do I say? Direct ancestor. Okay, this is parent, and after some time you might reach representative. This is representative of A. If this is A, this is parent of A. Right, so you find representative of A, you find representative of B, right? You check they shouldn't be equal. When you're merging 2 and 5 here, again, when you're merging 2 and 5 again, you see that representative of 2 is also 1 and representative of 5 is also 1. So it won't be merged basically because it's already merged, right? So you leave it there. If it's not that, you make parent of B equals to A, right? Remember the initial case. 1, 2 and 4, 5. Right, we are merging 2 and 5, right? We did find set of 2, So representative of 2 was 1. Similarly, representative of 5 was 4. Now you made parent of A equals to B, basically. Or parent of representative of A was 2. Parent of, or B equals to A, anything, right, for now. So parent of 4 you made as 1. So basically this got attached here. That's all. That's all for union. You just check that they shouldn't be in the same set first. If they are not, you make parent of B equals to A. That's all.
So, but in this case, like both the trees are in the same array, right? Both of them are in the parent array.
Sorry?
Both the trees are in the same array, right?
In the same array, in the sense?
Uh,
Like this
so
case?
like uh, so like one and two will be what I was assuming was ki one and two will be in its own array and four and five will be in its own array, and then you have to like create a new array to merge them. But that's not the case, right? In this one.
No, I didn't understand. Why are you creating arrays? There's just one single
Sorry,
parent.
yeah, the parent array. Yeah. So I thought one and two का खुद का parent array होगा and four and five का अलग parent array होगा
See, the
ऐसा.
array is same, just the values change, no? For
हाँ,
1, the
now I
parent
understand.
is 1. For
One, two,
2,
three,
the
four, five पूरा बनेगा, right?
yes. See, this is the, before merging this 1, 2, and 4, 5, this was the original array.
Right. Understood.
Sorry, 4's parent is 4, 5's parent is 4.
Yes.
Right. When you merge it, the parent array changes like just this 4.
Yeah, it will
Just this
become
4
one.
changes, that's all.
हाँ.
It becomes 1.
Five का.
No, 5 won't change. Parent array I'm talking about, not
Okay.
representative.
Okay. Understood. हाँ.
Right. So see, initially when you try to poll 5 to find the set, you go to 4, you come back to 4, you say, okay, the representative of 5 is 4. Right. Now what happens?
Right.
Now this 4 changes to 1, right? Now when you try to poll for representative of 5, it goes to 4, 4 goes to 1 now. 4 doesn't stop there because you changed its parent, no? And 1
Right.
goes to 1, and representative of 5 now becomes 1. Right. Understand how this recursive function is working. Right. And how changing the parent of your representative changes your entire representative. Right. Initially 5's representative was 4, but now we merge it to 1. Now it goes one more iteration deeper. Right. It goes one more call deeper, and it polls 1 back to 5, saying that parent representative of 5 is 1 now. I'm giving you 2 minutes. Ask me doubts. Again, the code looks pretty
ये-
simple.
इसका application क्या है?
There's a lot of applications. See, you can merge things in constant time. Okay, right now we have not completed the entire implementation. Right, so you can
Okay,
merge
okay.
different sets in constant time. It's so powerful.
Okay, that's interesting. Yeah.
Yeah, let's say you have a set of like 100 and 100 elements, right? If you wanted to, let's say, merge both of them naively or in a brute force way, you'll take at least 100 iterations, right, to merge entire thing. But right now
Yeah.
with DSC, you can just do it in a single step. You just merge the
Oh,
parent.
right. Yeah, you just merge the representative. Yeah,
Yes,
that's nice.
that's all. Okay, so if you don't have any doubts, okay, there is a case where, let's say, 1, 4, 5, 7, 9, 2, right? Let's say you have a chain that is n length, skewed. You have a bamboo, it's called bamboo. A tree that has just single child until the leaf, it's called a bamboo, right? Let's say you have a bamboo of length n, right? So what is the time taken to find the set of the leaf? Let's say find set of whatever last element is there, let's say 2. Can you realize it's on?
Yes.
Right. And if I ask you the same query, please find set n times, it's on square. Right. If I ask you n times, right, it's n square, which is bad. Right. So we do one very small modification. It's a very small modification, and it changes the entire scenario. So what we do is, whenever we find the answer once, whenever I call this once, here I'm calling it n times, right? Let's say the first call I found the representative of 2 is 1. So what I do is I make its parent equal to 1 as well. So the tree changes like 1, and 2, right? But can you realize something? The find set function that we wrote, was a recursive function, right? So whatever happens to one node happens to all the other nodes as well. You will understand it when I show you the implementation. But what actually happens is, when you call find set of 2 just once, the tree changes like this. And I'll ask how. See this code. Until now you were just returning find set of parent, but now you are changing the parent to whatever you are getting from here. So I'll show you, I'll dry run an example and show you. Right, so you called find set of 4, right? You called find set on 4, right? 4 goes to 3 and asks him, oh, what is this set? Can you call find set of 3, right? So this parent of 3 is not 3, it goes up, calls find set of 2, it goes up here, right? It asks find set of 1, so parent of 1 is equal to 1, so this will return it 1, right? And parent of 2 becomes 1, which was already there, so it's not a problem. Why does it become 1? Because for find set of 2, or let's say for find set of 3, what happened? It checked if 3 was equal to parent of 3, which was not the case, right? So it did return parent of 3 is equal to find set of parent of 3. What is parent of 3? Currently it was 2, right? Now can you realize what happens? What will this 2 return? It will return 1, right? So technically what happens? Parent of 3 equals to 1, plus it returns this 1 as well. Back again, you return, do you remember writing dp? Return dp of I is equals to whatever return value. So what happens? This initializes it as well, plus returns it as well, right? So parent of 3 now becomes 1, so this link is broken, right? And it attaches to 1 directly, right? And what will find set of 3 return? It will also return 1, right? So 4 breaks its link and attaches itself to 1, right? So the final tree looks like 1 2 3 4. Any doubts on this? Just take a minute, understand it. It's just 3 lines, and the change was just 2 words, right? But it's an immense change.
Yeah, can this be done iteratively?
No.
No? Okay.
You can do it with while, I guess. Yeah, while v is not equal to parent of v.
So will that be faster or will this be faster?
Makes no difference actually.
No difference.
When I tell you the final time complexity, you'll understand this makes no difference.
Understood.
So I think, let's say you're trying to find set of v. So while v is not equal to parent of v, no, but how will you do it iteratively? You cannot assign everything, right? You need the recursive call as well. See, if you do it iterate, this is called path compression. You cannot do path compression if you do it iteratively. You can just write v is equals to parent of v. That's all. Right. So ultimately this loop will break when v is equals to parent of v, right? So basically, if it's 1 2 3 4, you called let's say v is equals to 4 initially. So v is not equal to parent of v, v becomes 3, right? Then 3 is not equal to parent of 3, becomes 2, becomes 1, then it breaks out. So ultimately v becomes 1, but you didn't compress the path, right? This path compression didn't happen if you do it iteratively. You need a recursive approach, right? Please ask me doubts. Parent of v is find set. Initially this was not there, so you were just returning find set. But now what you are doing, you are also assigning the parent, you are changing the parent, right? So every time you call a bamboo, every time you call a bamboo, right, every time you call find set on the leaf of the bamboo, the whole thing changes into a star tree. Is this understood? Everything reassigns itself to the representative. Any doubts you ask me right now? Right, so this optimizes your find set function, right? So meaning that if I perform same n queries on find set of n, where let's say the tree is a bamboo from 1 to n, so a bamboo from 1 to n, basically like this. So in the first query itself, it will become a star tree, right? Next time you call find set, it will just directly print the array value, right? Because it's right next to the representative, right? Now the parent of n is actually equal to the representative of n, right? Just after one find set function. So if you call this n times, first query is going to take n, right? The other queries are just going to take constant time, right? So basically it becomes O of n. Right. Any doubts in this? Is it clear? There is one more problem, okay, with this. Now, okay, you optimize the find set function, right? But how will you optimize the merging now? Because merging is still a problem, right? You are just randomly assigning A, B like this. What if A is a very small tree and B is a huge tree, right? And again, you merged it with some other tree where the first tree was very small. Let's say this becomes B. Now you merge it with another tree, right? Now what happens is, okay, you compress the path, so it will take O of n time just once, right? But again, what can happen is, you can again create the tree like this, no? Let's say you had 1 2 3 like this, right? Now you attached 4 here, you merged 4 and 1, it happened like this. But because you are merging by 4, 4 was A is equals to 4, and let's say B can be anything from 1 to 3, let's call it 1 itself for simplicity, right? So this tree becomes big, but let's say you called find set on 3, and the tree now becomes 4 1 3, right? Now again you merged it with 5 6 something like this, 7. Again you called find set on 3, right? So this took, let's say, 4 operations, right? This will take again 4, this will take 5 operations, but again it will become a star tree, okay? But somehow can you understand that this is still a time complexity that you want to decrease, right? And on average case, after path compression, the time complexity becomes O of log n, right? And I won't be explaining the log factor here. It's from small to large merging, right? It's altogether a different topic, right? So right now you have achieved O of log n, which is still remarkable, because you can do things in O of n log n time, right? Actually, don't try to understand the time complexity too much here. Just get it intuitively, and that's fine, because the time complexity is really complicated for DSU, right? So okay, there's still a problem is what I'm saying. Like, what I'm saying is, let's not just randomly merge, let's find some heuristics. Like, if there is a very small component, there is a very huge component, right, a very huge set, it's not feasible to merge it like this, right? What I'm trying to say is we should be merging smaller elements to larger elements. That's called small to large merging, right? And that's called union by size. Right. So what I'm trying to say is instead of merging a smaller element to a really large element, let's do it other way around. Right. Let's say this was one component, right, and this was other component. Now tell me which tree is more optimized, this or this. This seems more optimized, right? Why? See the height of the tree. Here the height is 5, here the height is 4. Right. So let's say you're merging a tree whose height is 15, right? Height of A is 15 and height of B is 200, right? So it will be more optimal to merge A to B, right? Because the height of merged component will still remain 200. How? See, this is, let's say, maximum 200 and here you just add 15. Makes no difference, no? 15 and 200. If you did it the other way around, right, it will become 201. How? This is A, 15, right? This is 201. Basically, this will also become 16, but that doesn't matter because 200 is already greater, right? So this becomes 201, which increases, right? So if you merged B to A, the height became 201. If you merged A to B, the height just remained 200. So what I feel is this is more optimal, right? So this is a principle of small to large merging. It says that always merge smaller elements to larger elements. Right, and this is called union by size in DSU. This is another optimization which brings the time complexity. Now, again, there is a very huge research paper written around it, the time complexity of DSU. It's called Ackermann function, okay, O of alpha of n, and Ackermann function grows very slowly. See, the Ackermann function for 10 raised to the power 600 is just 4. Right, so it's nearly constant. So basically, Ackermann function is how many times you need to log a number, how many times you need to perform a logarithm on a number such that it becomes 1. Right? It's not log 2 of n basically. It's not the log value, it's like a number of times you perform the log. Right, so let's say for 16, right, it becomes 4, 2, 1. Right, so log 2, 16, 4. It's 2 and log 2 is 1. So 3 is the value of Ackermann of 16, basically, something like this. It's something close to it, it's not exactly this. Right. So this is union by size. Okay, even if you don't understand the technicality, it's alright. No one is going to ask you the technicality. Just understand that you always merge smaller elements to larger elements, always. Right. If you want to read about it, there is something called small to large merging. It's a really interesting topic. You can go read about it, right? So ultimately what I'm trying to do is for merging in DSU, I am merging small to large. For finding set, I am doing path compression. Right, so path compression reduces the path. Small to large merging makes sure that your merging is optimal. Right, so both of these combined, okay, both of this combined is inverse Ackermann function. Right, sorry, just Ackermann function. Right, both of these combined. Don't really dive into how this comes up, okay, but just understand, just can you intuitively understand that these are going to give you something optimal, right? These are good optimizations on DSU. right? So I'll give you the final code, and I'm referring CP algorithms, right? And I'll give the link as well. Okay, you can refer almost all algorithms here, they are really good, right? So this is union by, again you can union by rank as well, but just both of this time and space complexity is the same, so you don't need to worry, right? So this is how you union by size. So the only thing is you have to maintain another size array, that's all. So whenever you make a parent, so each set is a parent plus the size is 1. So parent of 1 is 1, size of 1 is 1. 2, same thing, parent of 2 is 2, size of 2 is 1. So when you merge them, what happens is parent of 2 becomes 1, parent of 1 is 1, and size of 1 is equal to 2. Right, now size of 2 here is 1, but it doesn't matter because this will never be polled. You will never be using it anyway, because you always find the representative first, right? And then if it's not equal to b, now see the part where small to large merging is happening. If size of a is smaller, right, so what does this do? This part is basically merging a to b, right? But what if a is smaller? What if a is smaller? So you basically swap these out, right? So you merge b to a now. That's all. That's this part is doing, and this is union by size. Union by size part. This is all, right? So make the parent, and of course you add the size, right? So if you're merging trees of size 5 and 12, right, when you merge them into a single tree, the size becomes 17, right? That's all.
So yeah, when the size array में when you merge them,
Yes.
it, whichever one was the smaller one,
Hmm.
उसमें 0 आ जाएगा, right? And the bigger one will have 17 then.
No, the smaller one will still have 5.
Oh, because okay, हाँ उसके नहीं, वो सब tree तो अभी भी है, okay, हाँ,
Yeah,
understood,
but the thing
understood.
is, you will never use it, no?
Yeah,
Every time
understood.
you're finding the set. So whenever you're trying to trying to merge B, first you convert B to A. How? You find it set, right? And the size of the representative is pulled. Always the size of the representative is pulled. How? You are finding the representative here. Remember,
Understood.
right? That's why.
So if the size array is not given, we'll have to make it ourselves, right?
Nothing will be given. You have to make both of these yourself.
Yeah. So size array तो ढूंढने में it will take n, right? Oh sorry, login हो जाएगा. हाँ, my bad, my bad. Yeah, never mind, never mind.
Yeah. Right. So actually, that's all the thing that you need to know for DSU, right? Now, if you see, the code size is really small, and if you understand each and every line, okay, each and every line is really important, right? If you understand everything, right, it's really small. You can write it in OS as well. And actually, DSU is very popular with Google. Almost every interview you'll have, like, let's say 2-3 technical rounds. In one of the rounds, you are sure you'll be asked DSU, right? So please prepare it well if you're targeting companies like that, right? And I'll tell you, once you solve few problems of DSU, right, it's so intuitive to understand, right? We'll discuss few problems right now, and then you'll understand. So intuitive. DSU is really intuitive, right? Right now I want you to understand how do you make it, right? How you are unioning it. Like here you are merging them by size, and there is the path compression. Right. These two things combined give you the time complexity of Ackermann function, which is nearly constant. So you don't even need to worry about that. Right. On average case, it's constant. Right. And always remember, do not confuse between parent and representative. Please. This is a very common problem for people who just start learning DSU. Do not confuse between parent and representative. Parent is not equal to representative unless you have called find set once. Parent of let's say V is not equal to representative of V unless you have called find set of v and you have not performed any merge operations on this tree again. So when you do this, what happens? Parent of v becomes representative of v, like how I explained earlier. So only then you can say that okay, parent of v is equal to representative. Otherwise, you cannot. Okay, one example is, let's say 1 2 3 4, right? Parent of 4 is 3. When you merge 1 and 3, this happens. Parent of 4 is still 3. Now if you call find set on 4, the tree becomes 1 2 3 4. Now you can say okay, parent of 4 is representative of 4 is 1, but here parent of 3 is not equal to parent of 4 is not equal to representative of 4, which is 1. Remember, just by merging you're not making them equal. You have to find the set at least once, right? If you have any doubts, please ask me right now. Discussed a lot of things. Again, this is one of the, how do I say, mathematically it's a bit difficult to understand because a lot of things are happening, right? Theoretically, just stick to theory, the trees that I drew in front of you, that's fine. Understand that small to large merging and path compression will affect its time complexity. Again, in interviews, don't worry, they won't ask you to prove DSU. Okay, it's good if you know it, right? But what you need to know is how small and large merging, like not even how, why you are doing this. It is going to help you in some way or the other.
Yes, sir. Bhaiya, can you explain that one again? Why small to large is better?
Okay, so take this tree. Also remember that height is a factor for time complexity a lot in DSU, because height determines the path for find set, right? Lower the height, less number of iterations or less number of recursive calls are made, right? So with this you will understand that decreasing height or a smaller height is always beneficial, right? So let's say you're merging these two trees. One tree, the height of this tree is 3. Let's call it A tree. Height of A is 3 and height of B is, let's say, identical. It's also 3, right? Or no, let's make it 4, right? Now tell me a better way of merging them such that the height is decreased. One way is merging B A here, this is one way. The other way is merging B to A, so this becomes A B, right? You can see that the height of the new tree here, height of this is 5,
This one is bigger, yeah,
right? And height of this is
4.
right. Now here you will just say that okay, it's this difference of 1, it doesn't matter. But if you keep on doing this unoptimized merging for n time, the height difference will be n, which is a big
Right.
factor, right?
Understood.
Again, see, you will argue that okay, but how does it matter? Because once I call find set, everything is going to shrink, right? But again, this factor is not huge. On an average, even if you don't do something like this, right? Even if you don't do something like this, you are going to get an average case of log n, which is not bad. Okay, this is not bad, but if you have some optimization that you can perform here, why not go for it,
Understood.
right? If you just do small to large merging here, this reduces to Ackermann function, which is nearly constant, right? That's all. That's about why small to large merging. Okay, I'll give a statement here, okay, about small to large merging. Again, this is not at all required for you to understand the entire thing, but this is a very good proof of small to large merging. So an element is only merged is only merged, this is a statement from small to large merging, when an element, let's say from a set, is only merged to a different set when the other set is larger, right, than the current set. Right. What does this tell you? Let's say the size of the first set was A. Okay, set A, let's say the size of set A was n. The size of set B was, let's say, marginally greater, n plus 1. Okay, so all elements of A will merge to B. Let's just say you're picking element by element and merging them inside here. I'm talking about small to large merging. This is not related to DSC. What is the size of the combined set C? It's 2 into n plus 1, right? Which is double the size of both the sets. Right, very intuitive to understand. Let's say both of the sets are almost equal. So when you merge A to B, the size becomes double. Right. So can you say that every time you merge an element, the size of the set becomes double than whatever its size was right now? Can you understand this statement? Whenever you merge, you make a set that is twice as large as what you were in right now. How many times can you do this? You can just do this log n times, right? So let's say your set size was 4, you merged it into 8, so you copied all 4 elements into this. You merged 8 into a set of size 16, you merged all 8 elements. Right, you can do this how many times? Until it reaches n. You'll just merge it log n times, right? Base 2. Right.
I didn't understand this part.
Okay. Every time you merge an element, or every time you copy an element to a different set, the size of the set increases by twice. Can you understand this?
A single element, is that what you're saying? Every time you merge a single element.
Yes, every time you merge a single element, let's say set 1, set 2. I'm talking about small to large merging. This is the explanation of small to large merging. So let's say there is an element A here, and the size of this set is n, the size of set is n plus 1. Right. So every time you have to perform an operation where A is copied to B, right, the size of the entire set becomes 2 into n.
Yes.
Can you understand this?
Yeah, that part I understood. I didn't understand log kahan se aaya.
Okay. Now see what happens. Now tell me, if you had to merge this again, what will be the size of set? 4 into n.
Yes.
If you had to do this again, the size will be 8 into n.
Right.
How many times will you do it until you reach some limit k? Let's say it's 10 raised to the power 5.
Oh, okay. Understood now.
That's log base 2 of 10 raised to the power 5, right?
Yes.
So basically what I'm trying to say is every element is just merged log n times. So the time complexity of small to large merging becomes n log n. Right, this is small to large merging. Please, if you don't understand, that's fine, you can leave it. Right, but this is the magic of small to large merging. Instead of merging each and every element again and again, right, you can just merge it log n times. So every element just gets merged log n times, basically.
Understood.
That's the whole idea of small to large merging. But the only thing that you remember is small to large merging improves or decreases merging operations. That's all.
Understood. So, but one doubt I had was, while merging, if you already know the representatives of both the trees, the merge part itself is going to be constant.
Yes.
The part that is taking time, or that we're optimizing the tree for, is the find representative part.
Yes, find representative. Yes,
Understood.
That's true.
Okay.
Merge is always constant because you're just making a change in parent, right?
Yeah, that's right.
Right.
Understood.
Here you have no loops or while condition, but here you do have it.
Understood.
Right, recursive. Yes. Right. So, quick problem. I'll realize the true power of DSU. Right. So first problem that we'll solve is most stones removed. Now again, there were a lot of ways to do it. Right, I did it in a different way. I saw a solution, they were doing it in a different way. Right, so I'll put this in notes as well. DSU is really interesting because you can use the same DSU in a lot of different ways. Right, so the question says, okay, don't read the question, I'll explain you the question. So the question says there are few stones placed on coordinate axis, right? Let's say there is a stone here, and there is a stone here, then there is a stone here, there is a stone here, right? Or wait, actually. Right, so this is the question, right? So let's say a stone is placed here, another stone is placed here, right? Another is here, here, and here. Now it says that you can remove a stone if there is an unremoved stone in the same row or same column, right? So let's say initially none of the stones are removed. Let's say I can remove this stone because this is in the same column as this, right? Then I can remove this stone because this is in the same row as this. I can remove this because it's in the same column. I can remove this because it's in the same row, right? So this is the maximum number of stones I can remove, right? That's 4. Right. Now how do you solve it using TSU? Is the problem.
You can make like you can make the trees such that stones that share the rows and columns
Yes.
are in the same tree,
Yes.
and then you merge the trees maybe.
Yes. 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 True. See, the number of stones is 1000. Right. So you can definitely write an O n square. It is going to be O 10 raised to the power 6, which is less than O 10 raised to the power 7. So it passes in 1 second. Right. So you compare each stone with each other stone, and if the stone share the same row or column, you merge them. Right. Now let's call the stones 1, 2, 3, 4, and 5. Right. You can see that let's merge 1 and 3 because they share the same row, right? Similarly, you will merge 3 and 4 because they share the same column. You merge 4 and 5 again because again same row, and 5 and 2 because same column, right? Now can you understand that all the leaves here can always be removed, right? Because
Right.
yeah, so there will be a certain order that exists where leaf can always be removed, right? Let's take some other example, right? Let's take the example of 1, 2, 3, 4, 5, 6. Now see, what I'm trying to tell you is you can just use some random stone in the same column and remove all the other stones. There shouldn't be a certain order that okay 5 needs to be there for 6. No, it doesn't matter, right? But what I'm trying to say is an order will always exist, right? The DSU tree for this will look something like, let's say you merged 1 with 2, right? Or let's take it the other way around. 2 was merged with 4, 6 was merged with 5, then these both were merged because 2 and 6 are in the same, or whatever you merged, all of them are in the same row or column. 2, 6, 5. Then when you are wanting to merge 3 with 2, you merge it like this, and 1 like this, right? So this becomes your DSU tree. Then always you can remove everything apart from the representative. That's all. Right. Now you don't have to determine in which order you're removing stones. You just have to determine what is the maximum number of stones you can remove. But there is a
So
problem.
the
Yeah. Go
The answer will be the number of representatives that we have, right?
No, that's what.
Okay.
See, there can be multiple such systems that can exist. What I'm trying to say is, right? Can you realize that this is a different component now? These four, and these do not merge with any of those the above component, this component.
Yeah. So they will make their own set, right?
Basically, you have to find the size of all the representatives. Here there are two
So
representatives, one this, and if that is 6, let's call it 7, 8, 9, 10, 11, right? So you have to find the size of all the representatives. So basically what you can do is, you can just read the size array and find whichever is maximum, right? So here 1 2 3 4 5, here 1 2 3 4 5 6, you'll get 6 as the maximum size, right? And then you can just print 6 minus 1. Why? Because you cannot remove the representative, right? You can remove everything else, that's all. So basically the answer is maximum of the size array after merging everything minus 1.
what is the question asking for? Sorry, I didn't.
The Okay, so the
Right.
question asks for how many stones you can remove, maximum number of stones that you can remove.
So why can't we also remove 7K
Okay,
stones?
I think you can just start with a single stone. Given an array of stones represents a largest number of possible stones removed. uh, every coordinate stone can be removed with shares. Okay, I think okay, it has to be all the components. So
Yeah.
yeah, so okay, sorry for that. You have to remove. So basically you will find all the representatives. So first representative is 2, other representative is 7. How do you find this? Someone tell me.
Like you will iterate through the parent array, and then
Yes,
2 ka parent will be 2, and 7 ka will be
yes,
7.
nice. So you just make a set first, right? Or I think you don't even need that, right? You iterate through parent array, right? And wherever parent of x is x, you can do answer plus equals to size of x minus 1, right? Because this means that that element is a representative, right? And the answer is removing that representative, all the elements can be removed, that's all.
We can also do, if we don't want to find the size, right? We can just, because we know the total number of stones, and we know that each
Yes,
parent will reduce to itself. So we can just count the number of parents and
yes,
subtract
yes,
that
yes,
from
yes,
total.
yes, that is a better answer. Nice. So basically you can count the number of representatives, right? And you can do n minus representatives. Yes, that is a better answer. Nice. So you can return this. Any doubts, please ask me right now. Right, with DSU it's so simple, right? You just do an n square loop, merge everything, right? N square loop,
So
merge, then count parent, count representatives, right? Print n minus representative, that's all, done. DSU is just like a
I was
boilerplate.
I was trying to think of the brute force, but brute force में गलत आ जाएगा आंसर शायद से. Like I was thinking we could iterate through a diagonal, and then
Diagonal.
so you iterate through the diagonal of the matrix, and uh, let's say you're in the very first cell, which is 0, 0. तो उसके row और column में जो भी हो सब निकाल दो. फिर next diagonal
No,
पे
but
जाओ.
then you
हाँ,
have to determine an order, no? Let's say
that's
you
what.
removed
Yeah,
everything like this, you removed this, and there was one element lying here
that's what.
that
So
cannot be
फिर
removed, right? That's wrong.
exactly.
Yeah.
So how do you do it in brute force? Is there any other way? DSU is the only answer.
I think DSU is the only answer because even if you try to do it in brute force, you need a certain order,
Yeah,
right?
that's what.
And where you have all four directions, I don't think you can establish an order.
Damn, bro, this is nice.
DSU is so powerful with this.
Yeah.
Right. DSU is also used in graphs, very common, to find connected components. Right. Let's say you have a random graph and you have to find which component. Like let's say you just want to find whether, let's say, this component u and this component v are in the same connected component or not. It's so simple, right? You just make a set out of all these, right? And you just check whether parent representatives are same or not. That's all. Right. So DSU actually reduces a lot of problems. The thing that DSU actually covers, and that is actually fascinating, is that it doesn't need an order or something, right? You can merge in any order, but the end result is going to be the same, right? That is the most powerful thing about DSU.
But can you like show the first example you took for this question?
First example, this one.
Yeah, in this one, can you like try and start from three once? I just wanted to understand. I understand the end result will be the same, but I wanted
Mm-hmm.
to visualize it.
Okay, so we start with 3. What do you want to merge first? Let's say you want to merge 1, right? Then let's say you try to merge 5 first. 5 merged with 2, then it merged with 4. Then you want to merge 5 and 3, so 3 gets merged here.
Like 4 and 3, right?
Sorry.
5 and 3 cannot be merged, right? Because they're not sharing a row or column.
Yeah,
Oh,
basically
but
4 and
you're
3 was
merging four.
merged.
Sorry.
Yeah,
Yeah,
but
I
the
understood.
representative was merged. Yes.
Okay,
So
done.
yeah, so yeah, actually the representative are different, but what I'm trying to say is the sets will be the same. You have the
Yeah,
same
yeah.
set.
Well, the end result is the result that we want is the same.
Yeah, see,
Yeah.
in the end, what you want is components in the set, right? Size of the set, right? Only these two things matter, right? What is the representative doesn't really matter, right? Because that can change, and you there's nothing you can. How do you say? Like it's not a useful information knowing the representative. Knowing the set size is something, right? Knowing the components, mutual relationship between components is what DSU establishes, and that is going to remain the same, right? So okay, this was one question. Now this is lead code hard problem, and just read this question. It's so simple with DSU again.
Okay, it's similar to one you did right now.
Hmm. They have the same pattern, all DSU problems almost, right? So the question says you are given few numbers, right? Now this is actually a graph problem. Okay, so you are given few numbers, and you can establish relationship between numbers such that they share any common factor, right? So 4, 6, 15, 35, right? 4, 6, 15, 35. You can see that 15 and 35 share 5, so you can make them a single set. 6 and 15 share 3, right? 4 and 6 share 2. So basically you have to return the maximum size of the component, which here is 4. Is it the maximum size of component, right? Yes. Return the size of the largest connected component in the graph, right? And remember that in DSU, like how do you identify DSU problems? In this, see, there is no relation between 4 and 6, 15, right? But they are still in the same set, right? What do you call that
That's
relation? You call that transitive relation, right? Where if A relates to B, B relates to C, that means that A also relates to C, right? So this transitive relation can be extended, right, to whatever lengths, right? So DSU can merge this transitive relations in a single go, right? That's the whole point of DSU. If you want to merge A with D, you don't have to go back to A always. You can just merge C and D, and you'll see that A is also merged to D, right? Like that is in theory. In programming point of view, always A is merged to D because A is the representative, right? Let's say let's take the other way around. Let's say representative is C, so you merge C to D, and because A, something like C A B was already there, and you merge C and D, but soon you realize that D and A are also merged in the same set, right? So everything in the set is merged. So D is merged with C A B, in a single go, right? So when you try to find the set of both of these, it will become the same, telling you that they are in the same set, right? But again, remember in this question, it was a transitive relation, right? It was not that all the elements should share in a set. All the elements do not share a same factor, right? But they share a transitive relationship. That's all. That's why DSU worked here, right? So how do you solve the problem? The number of elements are 10 raised to the power 4. Right. Think about this. Right. In this problem, you can do something like this. Okay, I'm not going to reveal the exact thing, because then again, it's mostly related to graphs. So this I'll put as a miscellaneous problem. But instead of merging something like 4 to 6, then you have to use an n square loop, right? Like you did for stones. Instead of doing that, how about you merge? You make a temporary node, let's say 2, and you merge both 4 and 6 there.
Yeah, like you can merge them with a prime factor,
Yes,
right?
you can. Yes, you can make a dummy node. Make 3, merge 15 to 3, of course. Then you merge 6 to 3 as well, right? So basically merging something like this, where the circled elements are actually prime factors. Like when you merge 35, right, it becomes 535. Basically you're merging 35 with 15, right? Something else. So you require something else. You won't just
Yeah,
require the size of component. You require size of component minus number of prime
prime
factors
factor.
in that
Yeah.
component.
Plus, like if you already have some prime factors given to us, तो उनको भी account करना पड़ेगा.
Yes. So think about this. Maybe you can make 3 arrays: parent, size, prime factors.
We can do one thing, right? Like all these given numbers are positive, right? So all the
Yes.
dummies we introduce, we make them negative,
Yes.
and in calculation we say check it. Okay, if this is negative, this is a dummy, and I convert it to positive for just the sake of calculation. Okay,
Oh.
fine. या तो negative से भी factor तो हो ही जाएगा वो,
No,
right?
no, but the negative thing is nice. But again, like you have to keep a count. See, but yeah,
I mean, in the end, you'll need to count them anyways because you'll need a counter to like subtract that value. Yeah.
But what if you don't even count those? Is what I'm saying. Let's say all the prime factors are negative, right? And all the numbers that you're merging are positive, right? So you just run the loop for positive numbers. No? Like how you count it is like you make a map of parent, right, and int map. Then you say for all the numbers, basically, because the numbers will be positive, you say map of find set of that number a of I plus plus.
Right. Okay. And A of I will be positive only.
Yeah, you're
Understood.
not counting prime factors anyway.
Nice.
Then you find the maximum out of this map. Right. Something like that. Lot of tricks. You can even store prime factor as a different one, and then just find maximum out of size of parent, or size of representative, or size of any a minus size of prime factors of a. That also works. This might be again, both of these have different difficulties. Like I think the difficulty is same, but the idea is widely different. So whichever you can understand, you can go with it. Right. Any doubts in this? Here I introduce a dummy node. Right. You'll see a lot of these in graphs. I think there's a lot simpler way to do this as well. There should be.
Hey, what if when we're merging two nodes, we merge the node which has lesser factors to the node which has a higher number of factors?
Yeah.
So basically, like if you have 15 and 3, you'll merge 3 to 15 and you'll make the representative as 15 because 15 has the potential of getting another factor with merging with another number which has a factor of 5, right? But then I don't think this will always work, because let's say you have some number with 3 factors and some number with 4 factors.
Hmm.
Now उन दोनों के बीच में एक फैक्टर कॉमन है, सो सबट्रैक्ट वन फ्रॉम बोथ. नाउ नीचे वाले में 2 बच गया एंड ऊपर वाले में 3 बच गया. बट यू इट कैन हैपन कि नीचे वाले का फैक्टर मर्ज करने का जरूरत हो जाए, एंड यू आर ओनली चेकिंग द रिप्रेजेंटेटिव्स, राइट? सो या.
Okay. See, I'll tell you one thing. Uh, in some DSU questions, you can actually skip union by size. Okay. If the answer wants you to union by something, okay, let's say union by, just I'm just giving you example, by greater number of prime factors, something like this.
Yeah.
Because even in this case, the worst case time complexity will be n log n. Right. If you do union by size, the worst case time complexity of O of n for the entire program I'm talking about, not for a single operation. Right. So both of those will pass anyway, right? Doesn't matter. So sometimes if you want to skip union by size, it's fine. The only thing is that the other thing should be helping you reach the answer. Because here if you see n is 10 raised to the power 4, right? So n log n is also really small. Right, if had n be 10 raised to the power 6, then n log n might be a bit skeptical, right? It might overflow, not sure, it might give you TLE, but with 10 raised to the power 4, n log n is really small, right? Now we'll just discuss one last problem. If you have any doubts, you can ask me. Right, so this is a code forces problem now. Might be a bit tricky to understand. I'll explain it to you, don't read the problem. Right, so look at the screen, don't read the problem. I'll put it in the notes first of all. It has a really nice name, where the pizza from Code Forces. So the question says you are given two permutations A and B. Okay, now remember what is a permutation? A permutation of n is numbers 1, 2, 3, 4, 5 arranged in some permutation of itself. Can be 3, 4, 2, 1, 5. Right. And another permutation can be 2, 3, 1, 5, 4. Right. Now what happens is, there is some guy in the question, there is always some guy in the question. So he makes a new permutation, and what he does is he picks either of the element from A and B from the same position. Okay, what that means is, if you want to place the first element, he'll either pick 3 or 2. Let's say he picked 3, here he picked 4, here he picked 2, 5, wait, that's not possible. 2, 4, 1, 5. Wait, I took a wrong example. I should take an example from there first. Basically what I am trying to do is C is also a permutation. Right, so let's take this example, 5, 2, 4, 6, 3. 1, 5, 2, 4, 6, 3. 6, 5, 3, 1, 4, 2. 6, 5, 3, 1, 4, 2. So what he did was he made a new permutation by picking either of the elements from A or B at the same position. So let's say he picked 1 at the first position, second position he has to pick 5 anyway. Out of 2 and 3, let's say he picked 3. Out of 4 and 1, he has to pick 4 anyway. He cannot pick 1 because that won't be a permutation now. Now he can just pick 6 here, and okay, this is wrong because he cannot pick he has to pick a 3 here, right? So he shouldn't be picking 3 here, he has to pick 2. So do you agree that this is a permutation? right? Now the problem is he forgot what this was. Okay, you do not have this, but what you instead have is a D permutation, which is either 0 or some element x. Right, now what does this mean? So here it's 6 and all zeros. So it means that where it's not 0, where it is not 0, it has to be that element anyway. If it is a 0, you can choose what it can be. Right, so basically see here 6 is fixed, and if you see from here 3 is fixed, and from here 5 is fixed. Right, because those are identical. Basically you have to report the number of such number of permutations that can exist. So here the answer is 2. I'll tell you how it is 2. Now see, either he can pick something like 2, 4. Can he pick 4? 2 he has to pick. Right, here he has to pick 1 and 6. No, he cannot pick 6. Just give me a second. In third case there are two distinct permutations, 6, 5, 2, 1, 4, and okay, I think I copied, okay, last element I copied it wrong, sorry. It's 2 here. Yeah, it's 2 here because 3 is already present. Right, so here also we have an option. Right, so one can be picking 2, 4, 2, 1, 4, 3, or 3, 1, 4, 2. Right, there are two possibilities here. Basically you have to tell the number of possibilities of C.
Yeah, I didn't understand what the D array or vector is.
D array is if it is X, it has to be that element in C.
Oh, okay. So it is like it is fixing the element.
Yeah, it is fixing the element. So basically if D
Understood.
of I is not equals to 0, C of I is D of I.
Understood.
Right, if D of I is 0, C of I is A of I or B of I.
Understood.
Then you have to count valid C of I's. Count valid C such that C is a permutation.
तो ये तो PNC का क्वेश्चन लग रहा है.
Kind of, yes, but there is some dependency that exists. Did you see these two elements?
Oh, right, yeah. They're not changing.
Yeah, y is not changing because I cannot pick 6 here. Because 6 is
Understood.
already picked. So the only option is 4. So if I pick 4 here, I cannot pick 4 here. So the only option is 1. Right.
And if we now it depends on the order then. So yeah, one thing I'm noticing is that in DSU questions, the answer is order dependent, and DSU helps you avoid that.
Yes. Yes. Yes, exactly. Can you see one thing? This is 2, 3. This is also 2, 3.
Yeah. So now if you choose 2 in the first one, so वहाँ पे 3 लेना ही पड़ेगा. So in PNC you would have taken 2 for multiplication, but
Yes.
the real value is only 1. Okay.
Yes. Now wait, just let me give you a simple example. But for examples are purposely made harder. 1, 2, 2, 3, 3, 2, 3, 1. And these all zeros. Count valid C's. If you pick 1 here, right, you cannot pick 1 here, so you pick 3 here. If you pick 3 here, you cannot pick 3 here, so you pick 2 here. This is 1. Right, another C is, if you pick 2 here, you cannot pick 2 here, so you pick 3. If you pick 3 here, you cannot pick 3 here, so you pick 1. Right, another example, A, B. So 1 2 2 1 3 4 4 3. D is again all zeros. How many permutations exist just out of this? How many combinations exist out of this?
This is just the first two, only one.
No, two, no.
Because if you choose one, दूसरे वाले में two ही choose कर पाओगे ना?
Yes, and if you choose two, you choose
Okay,
one.
हाँ, two. Sorry, yeah, my bad. Yeah.
What I'm trying to say is, and how many were here? Two again.
Right.
Can you understand that these are connected components? There are two connected components.
हाँ, like a zigzag pattern. One
Yes.
का two, and then two से two, and two से three. Yeah.
Yes. So what happens when you fix one element of the connected component? Everything else is fixed. Right? Irrespective of what element you fix, everything else gets fixed because they are interdependent. Here if you fix 3, right, here if you fix 3, you cannot pick 2 here, so you have to pick 2 here. So if you pick 2 here, you have to pick 1 here. Remember, A, B is also a permutation, C is also a permutation. So it cannot happen that if 2 appears here, 2 appears somewhere else as well. Right? So if it's...
So the answer would be something like the number of representatives we have, and each representative can have two particular states, right? Based on which value you put.
Yes, so it's
Understood.
2 raised to the power representatives, right?
Yeah.
Again, or basically 2 raised to the power connected components, right? Again, why? Because in a single connected components, you just have two different combination of elements or two different valid C's that you can put. How? Because everything is interdependent. You fix one thing and everything else gets fixed. Right? Had it been something like, let's say 3 2 2, which is not possible, again I know I'm drawing it just. Right, here if 3 is fixed, right, here if 3 is fixed, you have to pick 1. Right, but anyway the answer exists here. What I'm saying is you just have one more option apart from that. Right, or something like, let's say 2 2 2.
Like in the example you've drawn in the very bottom, उसमें ऐसा है.
No, the example I'm trying to give is, if you select 3 here, you cannot select 2 here, right? So you have to select 2 somewhere else, right? Or it's something like 3 2, and let's say there is some 2 here. So if you have selected 3 here and you didn't select this 2, the only way C gets a 2 is from the other 2 of B. Right, remember C gets a number either from A or B. So if you already rejected a number from A, you have to necessarily pick the number from B, because C also has to be a permutation. Right, so if X is rejected from A, X has to be picked from B. Can you get this idea?
Yeah.
Right, so if you pick 3, this fixes 2 from here. If you pick 2, if there was a number X, this fixes X from B. Right, and ultimately there will be a 3 which will fix this 3. Right, so not only will these fix, these are forming a cycle is what I'm trying to say. This is an exact sum question for finding the number of inversions in an array. I'll tell you how when we reach graphs. This is more like a graph problem. Again, trees problems are very closely related to graph problems as well.
It's like you're trying to find a number of islands in a graph.
Yes, connected components basically.
Yes.
Okay, so now the question arises, what if D is fixed? So the whole thing is, first you find connected components here. right? First you find the connected components. Then what you can do is, let's say, and a valid C will always exist with respect to all A, B, and D. Now what I'm saying is, if at least a number of the connected component is fixed, you have no option, right? So basically this connected component is nullified because you have already decided what number should be there for this connected component, right? So what I'm trying to say is, if there are three connected components in this problem, one connected component is fixed because of x, so here will be some k which is already fixed, you cannot change. Now this y and z belong to the same component, so the connected components become just one independent connected components, which is just this, right? So the answer is 2 raised to the power 1, that's 2. Or if you want me to explain it with an example, if you look here, one connected component was 611446. This was a connected component. 5 is a connected component, and 2332 is a connected component. One thing, you can ignore all the connected components of size 1. A connected component of size 1 is both the elements same, so you have no option anywhere. So you ignore this, right? You see that this connected component is already fixed, you ignore this connected component, you just have one connected component left. So 2 raised to the power 1 is 2. Right. If you want, I can take any other example as well.
Where
Hmm.
in the example you drew y and z wala.
Sorry, I
इसमें
drew.
the y and z example, this one
Yeah,
on the very bottom.
yeah.
इसमें why are you doing 2 power 1? Shouldn't it be 2 power 2? Because y and z are also one component together, right?
But they are fixed, right?
Oh,
That's
they're
not.
fixed. Okay.
Yeah.
Oh, DB, they're fixed. Okay, okay, okay. I thought you were labeling them as y and z. Okay, okay, okay.
No, no, they are fixed. So one more example, right? Okay, same thing. A. Oh wait, everything is fixed here. Yeah, here nothing is fixed. So A, B, C. So 1 2 2 3 3 1 4 7 7 4 and 5 6 6 5. Three connected components. Each connected component can have two different permutation. So 2 raised to the power 3 is 8, which is actually the answer. Right. Let's take an example with few fixed. So the answer for this is 2. A, B, C. So 1 3 1 3 3 5 5 7 7 1. So it's this, 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 right? But the fact that 1 is fixed, 7 is also fixed, 3 is also fixed, 5 is also fixed. So basically this whole connected component is fixed. Doesn't matter if 1 is fixed or all is fixed, right? Even though 1 is fixed, you do not even need to fix these are already fixed, right? Another component formula is 2 6 6 8 8 4 2 4. So basically all the remaining elements are another connected component, and none of them are fixed. So it's again 2 raised to the power 1 is equals to 2. 2 is the answer. Right.
So, like,
Yeah.
how will we implement the DAC on this? Like, how will we merge the sets?
Yes. So merging is like A of I merges with B of I. That's it.
Oh, right. Huh? Okay, okay. Yes, that
Right.
makes sense.
1 merges with 2, 2 merges with 3, 3 merges with 1.
Like,
This
huh,
merge
okay,
will
sorry.
won't even take place actually.
But then, how will you merge like two A of I and B of I, the fundamental sets? But like, how will you merge between two of those, like two and three and 1?
Okay. Okay.
Yeah.
Mm,
you could like what I was thinking was you always keep the representative as one of the arrays, and you always merge from one of the other array. Then that's a like if you're making one and two, you make two the representative in the very first round, and then when you're iterating through the other components, you always check the top one because अगर जो नीचे आ चुका है वो ऊपर ही आएगा, वो नीचे
Okay.
वापस कभी आएगा नहीं.
Nee, see, but what is the problem with merging 1, 2, 2, 3? You can just merge the numbers as well. It's fine. So basically, you get a tree like this, no?
Yeah, but then how will you know कि one like two three depends is supposed to be merged with one and two if one is the representative.
No, I didn't get a question.
So like if initially if you have one as the representative, right, it will be
Yeah.
one and two. So
Yeah.
one will be on top and two will be on bottom.
Hmm.
Now when you read two and three, you'll just get two and three. So but your components, so you've stored in the form of the representatives, right? Like you've stored instead of storing one and two entirely, you must have stored only one, right? So how will you know
No,
if
no,
two
no,
and
no.
three belongs to one?
How storing one? I didn't get you. I stored 1 and 2 separate.
Oh, so you're storing the entire components. Okay, okay, okay. Understood.
Yes, I'm storing that as a single number. I don't
Oh, in
even
the
care
parent array.
whether
Okay, never mind. Yeah, yeah, okay, understood,
I
understood.
don't
फिर
care
parent
whether they're in
to
A or B.
parent,
Doesn't matter.
yeah. Okay, so for each one, you'll just basically find क्या कहते हैं, the representative to the parent array every time, right?
Yes, yes.
Okay, okay. I was thinking we'll do that constantly by doing some optimization. Okay, cool.
No, that's not a problem. Now see what you'll do is basically for this example you'll form these three trees. Right. Now let's say this was fixed and this was fixed. Right. So if this was fixed, let's say some x, what you'll do, you will find x. See, first of all, if this is fixed, this is either this or this, no? So what did I say? D of I is either A of I or B of I. And if A of I and B of I are merged together, they are the same tree. Right. So basically you find the parent of D of I, right? And how I solved it is I took a set int, right, and I inserted all the representative first. Firstly I merged A and B, I found all the representatives, I put it in set. Then every time D of I was fixed, I erased the representative of D of I. Can you understand what I did? I just deleted its representative. So for this problem, it will just be deleted once because this entire 1735 is a single tree. Can you understand what I did? Then basically the answer becomes 2 raised to the power size of set. See, if you're not able to understand, let's say I had 3 trees, 1, 3, 4, 7, 5, 6, right? Now let's say 3 was fixed and 5 was fixed, right? So initially when I was merging everything, my set will contain 1, 4 and 5, right? Now when I reach 3, I'll find the set of 3, so representative 3 is 1, I remove 1 from here. Let's say even 2 was fixed, I find the representative of 2 which is 1, I remove 1 which is already removed, so it makes no difference. I find the representative of 5 which is 5, I remove 5 from here, right? So set just contains 4. Basically set just has 1 connected components, so 2 raised to the power size of set will give me 2 as the answer, right? So that's all. That's the solution. You can maintain a set of representatives.
Uh, what if like again we can do the negative thing here as well, right? Because all the numbers that they're giving are from one to some value. Uh,
Yeah.
the representatives, let's say, so below 3 d can be कुछ filled था. So let's say that for that particular value it was filled. So when you're finding the parent for it, no, you can set the parent to its negative value. And when you iterate to the parent array, you check if p of x is equal to absolute value of at p of
Okay,
x,
okay.
and then if it is oh wait, no, okay, it should be equal to absolute value and it should not be negative, and then you take that one with and multiply with 2 and the sum value.
Okay, well, don't try to modify the parent array, but it might, yeah,
Oh, you're right. It might,
DSU might go wrong.
yeah, yeah,
Remember the
understand.
find set function, the recursive
Yeah,
function?
yeah,
That might go wrong, right? Because parent of 1 is now minus 1.
right.
But try
And
to
then
find
आगे
parent of
minus
minus
2
1.
forget to जाएगा.
Yeah, it will
Yeah,
go out of bound.
understood.
So, this was all. Now, DSU is very popular in minimum spanning trees in graphs, right? And there you'll realize that MST is just sorting plus DSU. DSU makes it so simple. That's all. You don't have to. I think this is Crystal, if I am not wrong. So in the other one, in Prims, you have to do Dijkstra over edges, which is very hard. But this looks so simple. This is actually really simple for MSTs. Right. So in short, try to understand DSU. If not the entire theory behind it, at least how it works and how you can use it. Right. And it actually helps in a lot of problems. All the order related problems where you can see some transitive relation. Right. You can just close your eyes and apply DSU and it will solve the problem. Right. Most of the DSU problems are just writing DSU, that's all. Then you merge it, then you find parent, find representative, count them, that's all. That's the whole problem. Here it was just counting the independent representatives, that's all. And this is 1400, 1500 rated problem. Right. So that's all for today. I kind of expect you guys to ask more doubts, right? Because unless you break your head, and I try to make it easy for you to understand, plus I take hard questions deliberately so that you ask more doubts, right? So unless you go solve problems, ask doubts, break your head twice thrice, keep asking doubts, it's really hard to understand it, right? I know few of you might not be understanding anything. Okay, it's fine, you can still ask doubts. I am ready to take extra classes as well if you are, if if you promise to put in efforts, right? So these topics are one of the advanced topics. All the topics that I taught previous months, they were building blocks of what I am teaching right now, right? So what I'll be teaching in this few days is what you might just directly get in your slot one OAs, right? So prepare it well. Basically, mostly DSU if you are targeting companies like Google, right? And I had a friend of mine, she was asked a really easy problem from DSU. It was just, the problem was screaming, I am just DSU, just say DSU and you will pass the interview. It was so simple. So please understand DSU really well, right? I'll put the CP Algo article there as well, right, which you can read, but don't try to read it fully again. Read maybe first few subtopics and that's all, right? Or you may choose to not read that as well because that is too very technical. Don't waste time there, right? And please solve the problems in practice sheet, right? It's not for you to solve in the holidays, right? Keep solving it every day. Yeah, Aditya.
Also, DSU can only be applied on I mean, sounds stupid, but it can only be applied on sets, right? Where the values are not repeating.
Not necessarily.
Okay.
You can modify the value, you can maybe normalize it, you can make them
So,
unique, something
so
like that.
like map them. Understood.
Yes, map them and you use it.
Understood. Okay. Cool, cool.
Yep. So, thank you guys. That's all for today. You can leave. Right. And please solve problems, please.